So, first of all, I'd like to thank the organizers for giving me the opportunity to have a contribution to this conference. Well, in my talk, I would like to discuss two objects or two procedures. Both of them concern periodic Hamiltonians with a countable discrete symmetry. And the first procedure, this is a propagator formula, and it is closely related to the Aharonov-Bohm effect. And the second one, this is the Bloch decomposition of such an operator. And I'd like to show that these two procedures are closely related, and in fact they are in some sense mutually inverse. So, as the celebrated Aharonov-Bohm effect has clearly demonstrated, the formalism of quantum mechanics is able to capture topological properties of the configuration manifold. For example, in the case of one solenoid and in the idealized setup, the configuration space is the plane with one omitted point, and this is a multiply connected manifold, and the fundamental group is just the group of integers. Well, there is a standard mathematical approach how to cope with such a situation. Let me denote by M tilde the universal covering space of M. It's basically unique. This is a simply connected manifold covering the original space. The fundamental group, I will denote it by the symbol capital gamma, acts as a discrete symmetric group on the covering space, and the vector space can be identified naturally with the original manifold. So, suppose so in that case, everything can be pulled back from M to M tilde. This concerns the gauge potential, and suppose we are given a scalar potential, the potential can be pulled back as well, and this way one gets a unitary equivalent Hamiltonian H prime. This is a gamma periodic differential operator, and it acts in the Hilbert space formed by gamma periodic functions on M tilde on the covering space. So let me now pass to the propagator formula. Probably this was discovered by Schulman in the framework of Feynman path integration. The idea is quite simple. One can notice that the set of all paths from, say, a point X to a point Y can be split into the homotopy classes. Each class is given by the winding number, how many times the path winds around the solenoid. And for each homotopy class, there exists a common factor, capital lambda of S. The homotopy classes are labeled by the fundamental group, and the capital lambda of S, this is nothing but the non-integrable phase factor, which is given by the winding number and by the magnetic flux through the solenoid. This is the language introduced by Wu and Yang. So, and this factor is common for each homotopy class, and so the propagator can be written as a sum over the symmetry group. More formally, we have a periodic differential operator, which is this one, and one can consider it either in this Hilbert space formed by periodic function. I call it in that case H prime, and curly K prime, this is the corresponding propagator. Or one can consider it in the space of L2 function, in the entire space of L2 function over M tilde, and the corresponding propagator is called K tilde. And the formula relates these two propagators. Now I'd like to pass to the Bloch analysis. For the Bloch analysis, what is needed, this is a well-defined Fourier analysis on the symmetry group. And there is a class of countable discrete groups which is known to possess a well-defined Fourier transform. These are so-called type 1 groups, and they are well characterized. This class covers discrete groups, this covers abelian groups as well as finite groups, but also more general groups. Unfortunately, there are manifolds, multiply connected manifolds of interest. For example, the plane with 2 or more omitted points, whose fundamental group doesn't belong to this class. Let me denote by gamma hat. So I restrict myself to this type of group. Let me denote by gamma hat the dual space to gamma, and by m hat, this is the Planck measure on the dual space. So what is the Fourier transform? This is a unitary mapping from the L2 space over gamma to a direct integral here. This is a direct integral over the dual space with the Planck measure. So lambda is a irreducible unitary representation. Curly L sub lambda, this is the representation space, and curly I sub 2, this is the Hilbert space of Hilbert-Schmidt operators. So the corresponding norm, this is the Hilbert-Schmidt norm. So if F is L1 summable function on gamma, then the Fourier transform is given simply by this equality. But the Fourier transform extends by unitarity to L2 integrable functions. It's unitary, it's given here, and there exists a formula for the inverse transform of as well. And here I recall that for type 1 groups, all irreducible unitary representations are finite dimensional, and even the dimension is uniformly bounded. Now, despite of the title and of my original intention, I will focus only on the case when the field strength of the gauge field vanishes. This is because of lack of time. This case is, as far as the notation is concerned, considerably simpler, and so more simple to present. And at the very end, I'd like just to announce that everything can be generalized to the case when the field strength is not necessarily vanishing. So the situation I'm considering is when M tilde is simply connected with a discrete symmetry group gamma, and the connection is flat. H prime is, and we are suppose also there is given as gamma invariant scalar potential V tilde. H tilde is the gamma periodic Hamiltonian, and because M tilde is simply connected, there exists a transformation, gauge transformation, which makes it possible to transform off the gauge potential, but the gauge potential cannot disappear completely for H prime. H prime is equivalent to H sub lambda, which is, as a differential operator, has this form. This is just minus Laplacian plus the scalar potential, so there is no gauge potential anymore, but the gauge potential appears in the boundary conditions. Now H sub lambda acts in the Hilbert space of lambda equivalent functions. So these are functions satisfying this condition. So they are not invariant with respect to the action of gamma, but instead it appears a factor lambda of S. This is the non-integrable phase factor given by the connection, and lambda is in fact a unitary representation of the symmetry group. And the Bloch decomposition says the following thing: there exists a unitary mapping which is explicitly constructed from the L2 space on the manifold M tilde into this direct integral over the dual space to gamma, called gamma hat, is the Planck measure. And the integrand, this is, I recall, curly L, this is sub lambda, this is the representation space. And here I denote by H, curly H sub lambda, this is the Hilbert space formed by lambda equivalent functions. And this unitary mapping decomposes H tilde into a direct integral over the dual space. So the components are exactly the operators or the Hamiltonians H sub lambda. And I'd like to consider also the evolution operator, and the corresponding evolution operator decomposes in the same way, like this, into a direct integral. So here I recall the construction of this unitary mapping capital Phi, but I don't want to go into details because there is not much time for this. So now I'd like to recall that the propagators should be understood as distributions, as distributional kernels of the corresponding evolution operators. So the existence of distributional kernels is guaranteed by the famous Schwartz theorem. So K tilde, curly K tilde, this is the propagator corresponding to the Hamiltonian H tilde. Let me recall just one more the notation. We are given a gamma periodic Hamiltonian, and if it acts in the L2 space over M tilde, then it's called H tilde, and if it acts in the space of lambda equivalent functions, it's called H sub lambda. And the distributional kernel for H sub lambda can be interpreted also as a distribution over the space M tilde times M tilde, but now with values in the Hilbert space of Hilbert-Schmidt operators in the representation space. So this is an operator value distribution. And this distribution, operator value distribution, is lambda equivariant in the following sense. Lambda is a unitary representation of the symmetry group. And the Bloch decomposition can be rewritten in terms of kernels. So given two test functions on M tilde arbitrary, so we have such a equality for K tilde, relating K tilde and K lambda. Again, the integral is over the dual space to gamma. Now I'm passing to the Bloch, to the relationship between the Bloch decomposition and the propagator formula. Suppose we are given a couple of test functions on M tilde, on the manifold M tilde. The couple is arbitrary, but otherwise it's fixed, but otherwise arbitrary. And let me introduce two functions. The first function is defined with the aid of the propagator K tilde, and this is a function on the symmetry group gamma, and it's given by this equality. The other function, capital G, is defined with the aid of the of the kernel of the propagator k lambda, and this is a function on the dual space gamma hat. So just recall once more that k lambda, this is a distribution with values in the Hilbert-Schmidt operators in the representation space. And these two functions can be shown to have nice properties. That means f is L2 integrable and g is bounded on the dual space, and it follows that it belongs to this direct integral of Hilbert spaces. Now the Bloch decomposition written in terms of kernels in fact means the following equality, that the function capital F is the inverse Fourier image of the function capital G. This is nothing but the Bloch decomposition, and because the Fourier transform is invertible, one has also this equality. That means that capital G is the Fourier image of capital F. And looking at this equality and rewriting it, or writing down what it means exactly this, that the propagator k lambda can be expressed as such a sum, and this is again once more the propagator formula. Thank you. So in this sense, Bloch decomposition and the propagator formula are related, and in this sense they are mutually, these two procedures are mutually inverse. And now, just at the very end, I'd like to announce that, so let me first say that this case of vanishing gauge field has been treated in this paper, but this can be generalized to the case when the field strength does not necessarily vanish. So gamma can be arbitrary type 1 group, in general noncommutative, and one can consider any smooth connection on M with arbitrary curvature, and everything can be generalized, both everything that means the Bloch decomposition, the propagator formula, and the relation between these two procedures. And to reach this goal, one has to employ a more involved geometric language of fiber bundles, which are not necessarily trivial, and also some additional algebraic construction, but that's all. I cannot go into details. Thank you for your attention.